Is that quantum entanglement? Wasn't the physics Nobel Prize this year on quantum entanglement? That's so cool. Can you tell me more about it?
Hi, I'm Rita. Hi, I'm Nayeli.
Hi, I'm Riley. And I'm Judah.
And this is quantum entanglement. So, what is quantum entanglement? Well, it's a phenomenon that describes the correlation between particles independent of distance. So, what you measure on one particle will be related to the measurement of another particle when they're entangled with each other. Now, for example, you can take a random number generator between 1 and 1,000. If you were to measure two particles that were entangled, both of their measurements would be kind of related to each other because they're within the same range. Now, if you were to separate those by light years of distance and still take those measurements on both particles, their results will still be correlated with each other. And you can do this no matter how far away they are from each other. Now, a good way to think of quantum entanglement is a superposition of states. Well, the idea of superposition is where you combine state A and state B into a combination, a superposition of state A, comma B. An example of this is constructive interference, where you have a sine function mixed with another sine function. It creates an amplified version of the sine function. Now, a way to apply that to electrons is that they have spin. Now, before you measure an electron, it's either spin up or spin down. Until you measure it, it is actually in a superposition of both states. You don't know if it's actually going to be spin up or spin down. Then you take the measurement, and then you reveal that one of them is spin up and the other is spin down in this instant that you take the measurement. So what you know about one, that when it's spin up, the Pauli exclusion principle will tell you that the other must be spin down.
Okay, so some more information on quantum entanglement is Bell inequalities. So in 1972, John Clauser and Stuart Frieda were able to create an experiment in which they showed the violation of the Bell inequalities. The experiment sent two entangled particles in opposite directions, which have polarization. When the particles are emitted, their polarization is undetermined. And all that is certain is that they have parallel polarization. This was investigated using a filter that allows polarization when oriented in a particular direction. If both particles were sent towards the filter at the same plane, then one went through and the other slipped too. But if they were right angled to one another, one would stop and only one would go through. The filter was then set at various angles and the results varied. This led to a correlation between measurements, stating that the likelihood of one particle going through depended on the angle of the filter paper that was testing the particle's partner's polarization at the opposite end. At some angles, the measurements violated Bell's inequality, therefore having stronger correlations than they should have if they had hidden variables were involved and the particles already had predetermined states, as seen. Then, in 1997, Anton Zeilinger conducted an experiment that demonstrated quantum teleportation, where one particle from an entangled pair collides with another and become entangled. They become entangled, resulting in the third particle losing its identity, but its original properties are transferred to that one particle from the original entangled pair. Electron teleportation is a way in which information from one system to another can be transferred without the loss of information. Then in 1998, entangled swapping was demonstrated by the Anton Zeilinger research group, in which two pairs of entangled particles used where one of the particles from each pair came into contact and the way that they became entangled. Each pair becomes entangled even if the pair never came in complete contact, as seen in the illustration.
So now that my colleagues have talked about the history of quantum entanglement and a bit about what really is quantum entanglement, I'll be talking about some of the experiments that have been done in today's world, and specifically the one I'll be talking about has to do with Space Quest, in which they really dive into quantum communication, which they do so through satellites. The first experiment that they do here it's carried out on the Canary Islands, which uses a 144-kilometer free space link. It's between these neighboring islands, La Palma and Tenerife, which is also known as Spain, where the European Space Association, they use a 1-meter diameter receiver telescope, which is used to receive a signal photons. single photons. In the second experiment, they used a laser ranging observatory from Italy, which was used to establish a single photon downlink from a low orbital in Earth satellite. Then a satellite to Earth does a quantum channel downlink, which is stimulated through the reflection of the laser pulses off the satellite and Aisha. What you can tell from these experiments is that space-based quantum communication is a source for entangled photons, which is suitable for space applications. Another experiment that is done is a preliminary design of a transceiver, which they call it a space-based quantum communication payload, which involves the source for entangled photons, which has onboard electronics, as well as true transmitter telescopes. The way that it works is that the two entangled photons are transmitted to two distinct ground stations via downlink, allowing for a test on entanglement, as well as it generates this secure quantum key, which means that the quantum transceiver in space is capable of performing two single downlinks using these onboard satellites, which allow for establishing two different secure keys between these satellites, meaning that one satellite can be in Tokyo while the other one can be in Vinaya. And this scheme allows for us to really demonstrate the first demonstration for global quantum key distribution.
Not only is quantum entanglement really cool, but it also has practical applications. Most of them involve information transfer, but here are a few. The first was cryptography. So like we talked about, once quantum particles have been measured, they lose their superposition state. So if you want to establish a secure key and tell whether or not someone has eavesdropped on this secure key for your code, you can see if the wave function has collapsed or not. So once that's received and the particles are still in superposition, both sender and receiver know no one accessed their secure key. Pictured on the right here, we have two images of a 17 nanometer high letter Q. So the left side uses entangled photons in something called a differential interference contrast microscope. The right side used to be the best signal to noise ratio that we could get, but using quantum entangled particles, specifically photons, then we could get that image on the left, which is more precise, less noise. If you want to learn more, get a better base for your study of quantum entanglement, you can take Chem 112 here at UC Merced. We discussed spin, this fundamental concept for electron entanglement that we discussed earlier. Like we said, due to the Pauli exclusion principle, no two electrons that are paired can have the same spin. They must have opposite spin. So these electrons can always be described using anti-symmetric wave functions. And this is the basis for this Pauli exclusion principle. These are the Nobel laureates for the most recent Nobel Prize. And together with them, we say thank you for your interest in this fun, exciting, invigorating topic.